In this video, we are going to introduce triple integrals. I'm just adding one more dimension, and there's no reason that I can't expand my work to integrals that involve three variables. And in fact, there's nothing that prevents me from expanding it to multiple variables and iterations of four or more integrals, depending on the number of variables I have. The basic ideas are going to be the same. It is the interpretation that differs slightly. Remember that a double integral involved adding up tiny bits of area, while the triple integral involves adding up tiny pieces of volume. The graph of a function given by w is equal to f of xyz, defined on a closed and bounded region D of the set of R3, will be the set of all points consisting of the coordinates x, y, z and f of xyz, where the point xyz is in the region D. There is no complete three-dimensional representation of this set of points, but we can still define an integral of f over d. We simply partition the region D up into n small rectangular boxes that can be ordered from k equal 1 to n, and this partition is going to include all boxes that are entirely contained inside the region D. The kth box will then have dimensions of delta x sub k by delta y sub k by delta z sub k, and the function value at an arbitrary point x sub k star, y sub k star, z sub k star in this kth box will be f of x sub k star, y sub k star, z sub k star. Just like one variable and two variable functions, I'm going to add up all these smaller regions that are entirely contained within my region D, and this will give me an estimated volume that will be less than the actual volume because I've only summed up the boxes that are entirely contained within the region. This gives me an approximation for my volume of the sum from k equal 1 to n of f of x sub k star, y sub k star, z sub k star times delta v sub k. Now if I let delta represent the maximum length of the diagonals of the boxes, we can take the limit of the Riemann sum as delta goes to 0 to obtain a triple integral over the region D. This triple integral over the region D of f of xyz dv is equal to the limit as delta approaches 0 of the sum from k equal 1 to n of f of x sub k star, y sub k star, z sub k star times delta v sub k. There are two physical interpretations for a triple integral. If f of x y is equal to 1, then the Riemann sum adds up to the volume of boxes in the partition, and the limit as delta goes to 0 gives me the triple integral over the region D dv, which gives me the volume of the region D. The second interpretation is that if D is a solid three-dimensional object and its density varies from point to point according to some function f of x, y, z, then the units of density are mass per unit volume. So the product of f of x sub k star, y sub k star, z sub k star times delta v sub k will approximate the mass of the kth box in D. If we take the limit as delta goes to 0, my triple integral will give me the mass of my object. So depending on how the problem presents itself, I may be looking for volume, and that's when f of x, y is equal to 1, or I may be looking for the mass of the object, which is when I'm going to have a function f of x, y, z that represents the density. Now, order of integration in triple integrals is still important, and when we have these, there are 6 possible ways to construct the order of integration. It still holds that just changing the order of the integrals and the order of the differentials will not give me an equivalent result. But in general, what we want to do is set up integrals that allow us to work from more complex expressions to simpler expressions. This means that we want our innermost integral to have the most complicated limits of integration, and the outermost integral will have the simplest limits of integration in general. So here is the formal definition of triple integrals. We'll let f be continuous over the region specified by D is equal to the set of all points x, y, z, such that a is less than or equal to x, which is less than or equal to b, g of x is less than or equal to y, which is less than or equal to h of x, and capital G of xy is less than or equal to z, which is less than or equal to capital H of xy, where g, h, capital G, and capital H are continuous functions. In this case, f will be integrable over D, and the triple integral is evaluated as the iterated integral, where the triple integral over D of f of xyz dv will be equal to the integral from a to b of the integral from g of x to h of x of the integral from capital G of xy to capital H of xy of f of xyz dz dy dx. Now keep in mind that this is not the only way we can set this up. We can change the order of integration in order to make things easier, but I have to be careful about figuring out what my limits of integration become when I try to change the order of integration. Let's work an example. I want to evaluate the given integrals and, if possible, sketch the region of integration. The first triple integral is the integral from 0 to 2 of the integral from 1 to 2 of the integral from 0 to 1 of y, z, e to the x dx dz dy. The second integral is the triple integral over D of xyz e to the negative x squared minus y squared power times dv over the region defined by D is equal to the set of all points xyz such that 0 is less than or equal to x, which is less than or equal to the square root of the natural log of 2. 0 is less than or equal to y, which is less than or equal to the square root of the natural log of 4. And 0 is less than or equal to z, which is less than or equal to 1. For a, the integral from 0 to 2 of the integral from 1 to 2 of the integral from 0 to 1 of y, z, e to the x dx dz dy is easiest to evaluate if I have an idea of what the region looks like to begin with. I'm going to set up my coordinate axes with the points x equal 1, y equal 1, and z equal 1 and 2 marked on the axes, and then I'm going to plug in my line from z equal 1 to 2 along the z-axis, and then from the bottom of that I'm going to plot a line from x equals 0 to 1, and then I'm going to plot a line for y is equal to 0 to 2, and then I'm going to construct a triangular plane that intersects those 3 points. This gives me a better idea of my region of integration. I'm going to integrate the inside integral first, the integral from 0 to 1 of yz e to the x dx, which is equal to yz e to the x evaluated from 0 to 1. This gives me yz times the quantity e to the 1 minus 1. This becomes my integrand in my middle integral, the integral from 1 to 2 of yz times the quantity e to the 1 minus 1 dz. Y and the quantity e to the 1 minus 1 act as a constant here, so my integral becomes yz squared over 2 times the quantity e to the 1 minus 1 evaluated from 1 to 2. This gives me 3y over 2 times the quantity e to the 1 minus 1. This is the integrand in my outer integral, the integral from 0 to 2 of 3y over 2 times the quantity e to the 1 minus 1 dy. This gives me 3y squared over 4 times the quantity e to the 1 minus 1 evaluated from 0 to 2. This reduces to 3 times the quantity e to the 1 minus 1. In my second integral, I want the triple integral over the region D of xyz e to the negative x squared minus y squared power dv, where my region is given by D is equal to the set of all points xyz, such that 0 is less than or equal to x, which is less than or equal to the square root of the natural log of 2. 0 is less than or equal to y, which is less than or equal to the square root of the natural log of 4. And 0 is less than or equal to z, which is less than or equal to 1. I need to determine what order of integration I want to use. And I'm going to notice that my exponent includes both x and y terms. So I'm going to choose to integrate with respect to z first, which will reduce my integrand to something in only x and y for the second iteration. Then I integrate with respect to y, and finally with respect to x. I'm going to sketch my region first. So I set up my coordinate axes with the key intercept points marked on x, y, and z at x is equal to the square root of the natural log of 2, y is equal to the square root of the natural log of 4, and z is equal to 1. Again, I have a line that goes from 0 to 1 in z, from 0 to the square root of the natural log of 2 on x, and from 0 to the square root of the natural log of 4 in y, and I can construct a triangular shaped plane that connects those 3 points. Now I set up my triple integral. The integral from 0 to the square root of the natural log of 2, of the integral from 0 to the square root of the natural log of 4, of the integral from 0 to 1, of xyz e to the negative x squared minus y squared, dz, dy, dx. Now that I have my triple integral set up as an iterated integral, I start with the innermost integral. The integral from 0 to 1 of xyz e to the negative x squared minus y squared power dz. This becomes xyz squared over 2 times e to the negative x squared minus y squared power, evaluated from 0 to 1. This gives me xy over 2 times e to the negative x squared minus y squared power. This is my integrand in my middle integral. The integral from 0 to the square root of the natural log of 4 of xy over 2 e to the negative x squared times e to the negative y squared dy. I've separated my exponential term out to make it easier to integrate this with respect to y only. This gives me x e to the negative x squared over 2 times negative e to the negative y squared over 2, evaluated from 0 to the square root of the natural log of 4. I plug in those limits of integration and simplify, and I get 3x times e to the negative x squared over 16. I plug this into my outer integral, and I get 3/16 times the integral from 0 to the square root of the natural log of 2 of x e to the negative x squared dx. I do that integration and I get 3/16 times negative e to the negative x squared over 2 evaluated from 0 to the natural log of 2. I plug in those limits of integration and it reduces to 3/64. This is the value of my triple integral over the region D. So now you get to try it. Pause the video and evaluate the given integral. If possible, sketch the region of integration. When you are ready, restart the video to check your understanding. I want to compute the integral from negative 2 to 2 of the integral from 1 to 2 of the integral from 1 to e of xy squared over z dz dx dy. I'm going to compute the innermost integral first. This is the integral from 1 to e of xy squared over z dz. This gives me xy squared times the natural log of z evaluated from 1 to e. I plug in those limits of integration and simplify. I get xy squared. This becomes the integrand in my middle integral, the integral from 1 to 2 of xy squared dx. This gives me x squared y squared over 2 evaluated from 1 to 2. I get 4y squared over 2 minus y squared over 2, which is equal to 3y squared over 2. This becomes the integrand in my outer integral. I integrate from negative 2 to 2 of 3y squared over 2 dy. I get y cubed over 2 evaluated from negative 2 to 2, which gives me 8 when I plug in those limits of integration and simplify. Now I'm going to sketch my region. I'm going to set up my coordinate axes with the limits of integration points marked on each of my axes. X is marked at x equal 1 and x equal 2. The y-axis is marked at negative 2 and 2, and the z-axis is marked at 1 and e. When I construct this region, I get a rectangular prism that lies above the xy plane and in front of the yz plane that has dimensions of 4 by 1 by e minus 1. This is my rectangular region of integration. This is how I can work with triple integrals. keeping in mind that in Cartesian coordinates, the order of integration needs to be carefully evaluated for each of the functions I might be given. Be sure and let me know if you have any questions.